Hello there, Mr. Sutton here, bringing you the BC Calculus 517 Extra Practice number 3 solutions on integration by parts. On this problem, there isn't really much else we can do with this product, so we're going to go with integration by parts. It's kind of the only show in town. So let's pick out, first let's write our formula. U dv integral equals uv minus integral v du. We have to pick out our u and our dv. Now, we have an algebraic and a trig here. According to my acronym LATE, algebraic is a better choice for u than trig is. So let me go with x squared for my u value. That gets nicer as I take more derivatives. Cosine, which I'm going to let that be my dv, cosine of x dx, that at least doesn't get worse when I take antiderivatives. So we'll be able to live with that. So my du is going to be 2x dx. Antiderivative of dv, v, is going to be sine of x. Multiplying across to get uv, we've got x squared sine of x. And then going this way now diagonally to get the integral of v du, we're going to have minus 2x sine of x dx inside our integral. All right, so we've got an x squared sine of x. That's good. Antiderivative of this, though, we can't do that in one step. That's going to take another round of integration by parts. So I'm going to come up with a new u and a new v value, a new dv value, rather. So my new u value is going to be 2x. I still prefer algebraic to trig when I'm picking the u value. And for dv, this time I've got a sine of x dx. Du is going to be 2dx. And v this time around is going to be cosine, or actually negative cosine of x. All right, so I've got my original term of x squared sine of x. That's not changing. Now I'm going to have a minus parentheses, and in here I'm going to put basically this uv minus integral v du setup again, using this stuff this time. So I've got a negative 2x cosine of x in there, along with a minus, actually it's going to be a plus integral of 2 cosine of x dx, because this was already going to be negative, and we have a minus integral here. So now we have x squared sine of x plus 2x cosine of x. And now we got to be careful here, because this negative is getting distributed. We can't hold off any longer. This would normally be 2 sine of x, but because of this negative, we're now going to have a minus 2 sine of x. And whatever plus c is going to be there, we always just write plus c. We don't have to write a minus c, because c is just a constant. It could be a negative constant too. We don't really care. It's just plus c. To take the antiderivative of this expression, this product, there isn't really too much we can do to make our lives easier in terms of simplifying. I mean, you could distribute the cosine of 3x to both things in this term, but it wouldn't help you because you'd still end up with an x squared times a cosine of x. Really, the only way out of this one is integration by parts. So here's our integration by parts formula. Integral of u dv equals uv minus integral of v du. Now we have to pick out our u and our dv from the original integral. And for that, I'm going to use my acronym LATE. So I have a choice between an algebraic and a trig here. Algebraic is a better choice for u, according to LATE, because a comes before t, or more theoretically, because we can take derivatives of algebraics, and trigs, they don't get worse as we take antiderivatives. Compared to the algebraics, we'd rather take an antiderivative of a trig versus an algebraic. So let's let u be 6x minus x squared, and then dv is going to be cosine of 3x dx. This is going to be a little bit of a mess here, but here we go. Du, that's going to be derivative of this. So 6 minus 2x in a parentheses with a dx outside. And antiderivative of cosine of 3x, that's going to be, let's see, we have to divide by this inner tail of 3. So that's going to be 1/3 sine of 3x. Multiplying across here, I'm actually just going to stick these next to each other without doing any kind of distribution. I'm just going to leave it like this. Now we multiply this way to get our integral of v du. So we have a minus integral of 1/3 sine of 3x and this parentheses here with a dx, all this stuff. And this is still kind of a mess. We need to do something with this, and there's no other techniques out there that are going to help us, so we're going to have to do another round of integration by parts. So here we go. Let's let our u value this time be 2 minus 2/3 x, because we have a choice between an algebraic and a trig function. dv this time is going to be sine of 3x dx. du, now we're going to have negative 2/3 dx. And for v, dividing by that inner tail of 3, we're going to have negative 1/3 cosine of 3x. So I have the original set of parentheses there. I'm going to have a minus parentheses now. And in that parentheses, I've got u times v. So this is, we have a negative 1/3 cosine of 3x. We have this parentheses with 2 minus 2/3 x. We have all this stuff. It's still a mess. And then multiplying this way now to get our integral of v du. So we normally have a negative integral. These two things both have negative signs. So that's 3 negatives overall going on inside this big parentheses. So that's overall going to be a minus integral of, now let's see, I can simplify this a little bit. This is 1/3 times 2/3. That's going to be 2/9 cosine of x dx. There we go. All right, cleaning this up a little bit, I have this original set of parentheses that I'm not going to bother distributing. Why would I? I guess I could, but I'm not going to. And then we are going to distribute this negative outside this big parentheses. So this set of parentheses here, we had this negative 1/3. I'm going to make all this stuff positive. So positive 2 minus 2/3 x times positive 1/3 cosine of x. And then over here, let's see now, I'm taking the antiderivative. I've got to divide by my tail of 3. So normally this would be minus 2/27 sine of 3x, but we already had a minus outside this parentheses. So minus becomes a plus 2/27 sine of 3x plus c. On this no calculator problem, we're trying to take the definite integral from 0 to pi of x squared times cosine of 3x. There's no way to really simplify this too much on its own. Since we have a product that we can't do anything else with, we're going to resort to integration by parts. So let's see here. We've got our general formula, which is going to be integral from a to b of u dv equals evaluation box uv from a to b minus integral of a to b of v du. Doesn't really get you any credit to write all this formula out here, but I think it helps to know where things are going. So we need to pick out a u and a dv from the original integral. Given my acronym LATE, L-A-T-E, A, algebraic, x squared, is a better choice for u than trig, this cosine of 3x. So we'll let u equal x squared, because I don't mind taking derivatives of algebraics. And we're going to let dv be cosine of 3x dx, because I don't mind taking antiderivatives of trig functions. They don't tend to get much worse. So now my derivative here, du, that's going to be 2x dx. Antiderivative of cosine of 3x, well, dividing by my tail of 3, that's going to be 1/3 sine of 3x. And now multiplying across here to get my uv that goes inside my evaluation box, that's going to be 1/3 x squared sine of 3x. That's going to be from 0 to pi. We'll have to evaluate that at some point, but we still have this integral to deal with. So multiplying this way now, we've got, let's see, this will be 2/3 x sine of 3x dx, all evaluated from 0 to pi. And this antiderivative is not a one-stepper. I still need to use another round of integration by parts on this one. So here we go with that mess. I'm going to let my u value this time around be 2/3 x. Algebraic is still a better choice for u than the trig function that I have here. And then for my dv, now I've got sine of 3x dx. du, we're going to have 2/3 dx. And for v, antiderivative of sine of 3x, that's going to be negative 1/3 cosine of 3x, dividing by that tail of 3 in there. So multiplying across now. So first off, I've got this original evaluation box of stuff, not changing that yet. Next, I'm going to have a minus parentheses, and in my evaluation box, this is like an inner uv evaluation box now. I've got, let's see here, negative 2/9 x cosine of 3x. So we'll have to deal with that in a little bit. And then multiplying this way now, we've got plus the integral of 2/9 of cosine of 3x dx. And moving straight across, I'm just going to actually end up putting all this inside one big evaluation box at this point, after I take this integral over here. So I've got the stuff that I originally had, 1/3 x squared sine of 3x. That hasn't changed yet. And now I'm going to throw also in this evaluation box minus minus. That's going to be a plus 2/9 x cosine of 3x. And now over here, I need the antiderivative of this stuff. So this would normally be positive 2/27 sine of 3x. But because I have this negative out here, this is going to be a minus 2/27 sine of 3x. And that goes in my evaluation box as well. I can put all these in the same box because they're all being evaluated from 0 to pi. Okay, well, I'm almost there. Now I actually have to plug pi into all this stuff and plug 0 into all this stuff and subtract. Now I'm kind of running out of space here, so I'm going to skip writing down a step. If I go ahead and plug pi into all of these things, let's see what I get. So I've got sine of 3 pi, which is going to be 0. So that zeroes out that first term. I've got cosine of 3 pi, which is really like cosine of 1 pi, which is negative 1. So this is going to be and I've also got a pi here. So I've basically got a negative 2 pi over 9 for that middle term in there. And then this last term, I've got sine of 3 pi, which is 0, so I don't have to bother writing that down. All right, so all we got by plugging in pi was just this lonely term here. Now, how about when we plug in 0 to all this stuff and subtract it? Well, if I plug 0 into this first term, it zeroes everything out. This second term zeroes everything out. If I plug it into this term, I've got sine of 0, which zeroes everything out. So really, when the dust settles, I just have minus 0 for that whole second term. So really, all I have is negative 2 pi over 9 at the end of the day for this one. Phew! For this one, we have the antiderivative of x squared times e to the x dx. Seems like it shouldn't be so bad, but if you think about it, there isn't really much you can do to take the antiderivative or simplify the product. So that's why we're going to have to resort to integration by parts, because there's really no other technique left. So that means I have the general setup of integral of u dv equals uv minus antiderivative integral of v du, so this setup right here. I need to pick out a u and a dv from the original expression. So using my acronym of LATE, L-A-T-E, algebraic, like the x squared, is a better choice for you than exponential, like this e to the x here, because I don't mind taking derivatives of algebraics. In terms of taking antiderivatives, taking the antiderivative of e to the x isn't going to make things much worse. X squared antiderivative, that keeps getting bigger and bigger, so I don't really like that. So I'll let my u value be x squared. dv is going to be e to the x dx. Derivative of u, du, is going to be 2x dx. And then antiderivative of e to the x is very conveniently also e to the x. So multiplying across here to get my uv, I've got x squared times e to the x minus, now I have the integral of 2x e to the x dx. And I can't quite take this integral yet. It's nicer than what I started with, but it's still not quite ready. So I'm going to have to do another round of integration by parts for this one. So this time around, my u value is going to be 2x. Algebraic is still better than exponential. That hasn't changed. dv is still going to be e to the x dx. And now for the du, I've got 2 dx. So this keeps getting nicer and nicer as we go. And then antiderivative of e to the x is still e to the x. So I've got my x squared e to the x term that I don't want to forget about. It's still there. And now I'm going to subtract in a big parentheses 2x times e to the x minus the integral of 2e to the x dx. So sorting things out, we still have x squared e to the x. Now we have a minus 2x e to the x. And the antiderivative here is also conveniently going to be 2e to the x. Now we have a minus here, and this other negative out here is being distributed. So that ends up being a plus 2e to the x there. And don't forget your plus c. On this problem, I'm trying to take the antiderivative of x squared sine of x. So one way you could try doing this is by taking the derivative of all these answer choices to see what gives you this. That's going to take a while. There's a lot of product rules involved in here. Another way, since there's nothing else we can do with this, is to try integration by parts. We've got a product that nothing else works on. It's integration by parts time. So my general formula, I've got integral of u dv equals uv minus integral of v du. I have to pick up my u and my dv in the beginning here. So for picking the u value, I'm going to use my acronym of LATE, L-A-T-E, which tells me that an algebraic, like x squared, is a better choice for u than a trig, like sine of x. So let's let u equal x squared, and then dv, the dv part of this, is going to be sine of x dx. And the key with dv is I want it to be something that I don't mind taking the antiderivative of, and this doesn't get too much worse when you take the antiderivative. So now taking the derivative of u, I've got 2x dx for that. And then for dv, antiderivative, that's going to be negative cosine of x. Multiplying across now to get this uv part, I've got negative x squared cosine of x. And then multiplying this way to get the integral part, this is going to be plus integral of 2x cosine of x dx. And I'm almost there, but this integral, I can't quite integrate that just yet. I'm going to need another round of integration by parts. So I'm going to let u be 2x this time around. Algebraic is still better than trig. And then dv this time around is cosine of x dx. So now this time around du is going to be 2 dx. So notice that keeps getting nicer and nicer as we go. Antiderivative of cosine of x over here, that's going to be sine of x. Now multiplying across to get the uv part of this. And by the way, I still have this initial negative x squared cosine of x. That hasn't gone anywhere. But multiplying across, we've got 2x sine of x. That's this uv part that we're adding on and splitting this up into. And then minus, we have integral of 2 sine of x dx. So there's just one more thing we need to do here. These first two terms are kind of locked into place, and we can't even combine them. This one, though, antiderivative of sine of x is negative cosine, so this becomes positive 2 cosine of x. And don't forget there's a plus c at the very end of all that. So this ends up being, let's see here, these first three answer choices all look very similar. But we need a minus, plus, plus kind of pattern here. So minus, plus, plus gives us choice C. For this one, I'm trying to take the antiderivative of x times secant squared of x dx. Now, this is one where we can't really use substitution or anything else that is going to resolve this quickly. So we're going to have to resort to integration by parts. So that'll be u dv integral equals uv minus v du. U and v dv, we have to pick those out in the beginning. Now, I have a choice between an algebraic, this x function here, and a trig, a secant squared of x. I'm going to go with the algebraic in terms of choosing my u value. That's according to my acronym LATE. A comes before t in that. But more theoretically, I don't mind taking the derivative of x. I don't mind taking the antiderivative of secant squared of x. So that's how we choose u and dv. So u is x, dv is secant squared of x dx. Derivative of u is going to be 1 dx. Antiderivative of secant squared of x, that's going to be really nice. That's just tan of x. And now multiplying across to get my u value, my uv value rather, I've got x times tan of x, which is fine. And then multiplying this way, we have the integral of, subtracting the integral of tan of x times 1 dx. Now, initially you're thinking, well, this looks kind of nice, until you realize, hey, I don't actually have a one-step antiderivative for tan of x, or maybe you do. Maybe you have that memorized. I don't. And if you don't know off the top of your head what the antiderivative of tan of x is, well, it's kind of like Wizard of Oz. If you didn't bring your broomstick, you're going to have to walk. We're going to have to find a more advanced technique for figuring out tan of x. So the key to unraveling this one is rewriting this as sine of x over cosine of x. If we rewrite it like this, we can actually treat this as like 1 over cosine as being an inner function. If we have an inner function whose derivative, which is sine, is somewhere else in the problem, we can actually use the substitution integration method. So I'm going to do some u substitution now. So I'm going to let u in this setting be cosine of x, in which case du is going to be negative sine of x dx. And then dividing by that, I can write dx equals du over negative sine of x. So substituting back in, I can rewrite this integral as sine of x over u times du over negative sine of x. Now I can simplify this to negative du over u. which is going to be a positive because I have a negative out there, so I can combine those negatives to give me a positive. So much nicer. And then finally, I can take the antiderivative of this stuff. This is going to be plus ln of absolute value of u plus c. Now, there's just one problem. That's not in any of the answer choices, and really, you should be suspicious if you have two different variables floating around at the end of one of these problems. But u was really just this cosine stuff here. So we can rewrite this as x tan of x plus ln absolute value of cosine of x plus c. So that was pretty wild. We needed integration by parts and substitution in the same problem. But at the end of the day, this is going to lead us to pick choice E. On this problem, we're trying to take the antiderivative of arcsine of x dx. Now, we already know the derivative of arcsine, but that's not quite what we need here. We need the antiderivative. And unless you know this off the top of your head, we're going to have to use some advanced integration techniques to do this. Now, the key to getting this whole problem started is thinking of this not just as arcsine of x, but thinking of this as arcsine of x times 1. This is a product, and when we don't know how to deal with a product, we kind of throw our hands up in the air and use integration by parts. So that's how we're going to handle this problem. All right, so our general setup is we have integral of u dv equals uv minus integral of v du. Now, for the u value on this one, I have a choice between, let's see here, this is a trig function, and we also have a choice between this and 1 for the u value. Now, normally, I would say, 1 sort of seems like an algebraic function, so we're thinking, well, maybe I let 1 be my u value, but it actually doesn't work out very well if you do that. You want the dv to be something that you can actually take the antiderivative of. If you let dv be arcsine of x dx, well, that was kind of like our whole dilemma here, right? We didn't know the antiderivative of arcsine. So really, if you're going to go down this road, the only logical choice, you're going to have to make u this arcsine of x. Because you know how to take the derivative of this, you do not know how to take the antiderivative of this. So that means our dv value, we're going to have to let that just be 1 dx. And, it's not getting nicer when you take the antiderivative, but again, if you're going down this road, there's no other choice to do this. All right, so derivative of u, this is going to be 1 over the square root of 1 minus x squared dx. And over here, antiderivative, we can at least take the antiderivative of 1. It's going to be x. So multiplying across to get my uv value here, that's going to be x times the arcsine of x. So that's at least in some of the answer choices. So this is a good sign. But now we have to do, let's see here, minus integral of x over radical 1 minus x squared dx. And we have a plus c that could be floating around there if you wanted it to be. But on second thought, maybe not. I could have it there. I don't need it, though, because I haven't actually taken the antiderivative of this stuff yet. So until I've done that, I don't really need that plus constant out there if there's still integrals left unresolved. So this is an issue. How do we even think about taking the antiderivative of this? Well, let's look at the answer choices and hope they gave us something that looks like this at least. Oh, wait, these answer choices are not fully integrated. In fact, there's an answer choice right here, choice E, that exactly matches what we just wrote. Well, we were just asking what this expression was equivalent to. It's equivalent to choice E. So yeah, we're just going to stop there, and apparently they didn't know what to do either. So we're going to be done.